Alright, we're on section 2.5. It's called polygons and convexity. So this section is going to have tons and tons of definitions. They're pretty self-explanatory. I'm going to go over most of them. But we'll start with two that you probably haven't heard before. And convexity is, you have two choices. You're either concave or you're convex. Okay, those are your two choices, and if you take a look at the picture, it has this picture that looks like that, and it also has the definition of concave at the bottom of the page. It says a concave set is a set that's not convex. So that one doesn't really help us any. Let's see what convex means then. It says a convex set has the property that any two of its points determine a segment contained in the set. That's how you know if you're convex. So let me just show you I'm going to read in section 2.5 here. It says all sets of points can be classified as convex or concave. It's easy to show that a set is concave. Concave sets always have some points that cannot be connected by segments without leaving the set. So they're saying it's easy to show that you're concave. So what you do is you choose 2 points. And first of all, concave could be started as a set of points. Okay, convex is also a set of points. So you won't ever have this is a concave point. It's the entire set as a whole. You'll decide if it is concave or not. So once you choose 2 points, you connect them with a line. Do you see how that line is still contained inside of, you're picturing this was all covered with points? Okay, and so I connected any 2 random points. This time, the segment that connected the points is still contained inside this area right here. But what if I chose this one and this one? Can you see that if I connected them, do you see how the segment that joins the 2 points leaves the area? So if that happens, you have concave. Okay, so it could look lots of different ways. This could be your area, and you'd have the same problem if you connected those 2 points right there. Anyhow, that puts you in the concave. To me, I try to remember it. If you just think about what a cave is, it's kind of like an, you go inside of it. That's what I think. So a convex set of points is something that's not concave. Or by definition, that if you had a shape, if every time, no matter what you chose, your 2 points and the segment that you draw between them is always contained inside of the figure, then you know that you have convex. So sometimes they look even, this is also convex. There's no 2 points I could draw anywhere and connect their line and have the line end up going outside of the area. That's what it means to be concave and convex. So example number 1, it says show that an angle, let me just squeeze it in right here, show that an angle is a concave set. Alright, so what they're meaning right here is that the angle, let me draw the angle. So the set of points that make up an angle are only the ones that are on this line. So I'm not talking about an interior of an angle. I'm talking about the angle itself. The angle is only comprised of this line and this line. I guess ray. This ray and this ray. But the ray is full of points. So if you take a point, okay, let's say this point, exaggerate it a bit, and this point, if you connect them with the segment, it has stayed as part of your original set of points, which are all the ones that form the angle. But if you choose one from this side and one from this side, and you connect them, all of these points that make up this segment are outside of your original set of points. So you'd have to say that this is concave. So the definition of convex is a set of points that has the property that any two of its points determine a segment contained in the set. So this segment is not contained in the set. Therefore concave. If you have more questions about that or need me to clarify more examples, I'll definitely go over those. You turn the page, section 2, we're on 2.5, so page 62. We have a polygon. All of this should go in your folders, but a polygon is simple, closed curve. All right, what does simple mean? That means it doesn't overlap itself, okay? Closed means it begins and ends at the same spot. So obviously it closes itself. And a curve is just something that you can draw without picking up your line, your pencil. Okay, so this isn't all of it because this is not a polygon, even though that was simple and that was closed. A polygon is a simple closed curve, and you have to have with segmented sides. Segmented sides. So segment is a straight part. So you can, that could be a polygon because it all has segmented sides. It's simple, it never overlapped itself, and it's closed. So we usually deal with polygons that look more like this. You know, a triangle. This one right here has 4 sides. So we'll talk about what that's called. But the other definitions that you'll see on page 62 is a side of a polygon. And it said it's one of the segments. So let's just take a look at this polygon right here. So a side is one of the segments. If you're going to look at this one, this could be a side. That's pretty self-explanatory. I think all of these segments are the sides. The next one is a vertex. It's the end point of a side. So here's a side. That means this is the end point. I think that's pretty intuitive also. These are all, if you try to say multiple, so you have vertex and you have vertices, if you're trying to say multiples. And then the angle of a polygon is, it has 2 properties. If you're wanting to find angle of a polygon. So first of all, let me just show you, it'd be that one right there. So the angle is going to be made up, okay, let me see, it's going to have this be one of its sides, and this would be its other side. So here's the angle. So the 2 properties that you have to have for an angle of a polygon is it has to have 2 of the segmented sides as its sides, and it also has the vertex of a polygon be its vertex. It's probably overkill. That's what it means. So example number 2 is going to ask you to classify all of these as concave or convex. So let's just, I'll draw these. There's this one, this one, this one, and this one. So concave or convex. I'm going to say this one looks like it's concave, and so does this one. I don't think I could draw 2 points and connect those with a segment that would leave the area. So we have concave, convex for these 2, and concave. Okay. Then we have this list right here that you're going to want to study, and it says number of sides and the name of the polygon and then a quick example. So we have the ones that we're going to be doing a ton. 3-sided ones are called triangles. We already knew that. If you have a 4-sided one, it's not always a square because what if they're not equal sides? So you have quadrilateral, pentagon for 5-sided, 6-sided is hexagon, 7 heptagon, 8 octagon, 9 nonagon, 10 decagon, 11 hendecagon, 12 dodecagon. And then if you have lots of sides and it's more than 12, whatever this number is, like say It's a 13. You could say a 13 gone. You just plug in whatever your side number is into your gone phrase. Anyway, here's just a few examples. It wouldn't certainly be an exhaustive list of all of those. Alright, so then we have the top part that's highlighted says polygons are curves. The interior is not part of the polygon. So let me talk about that for a second. Let me do a simple triangle. The polygon is this part itself. If you were to grab a polygon and pick this up right here, if you grabbed it and held it up, it would be empty on the inside, and it would just simply be this orange. It'd be kind of like an orange bracelet, a very small one, an orange triangled key ring. It would just be the orange part. You wouldn't pick it up and it wouldn't have a white interior. Okay, the polygon is only the segments. That's it. So once you start saying you want to include maybe all the points that would make up a solid area, and including this, including the triangle itself, plus all the interior, you end up with what we called a region. A region is the polygon plus the interior. That's what a region is. We learned what a region is last time, but we said a simple closed curve and its interior. Now we're just going to say region in this case is the polygon, so the outline and its interior. Okay, we have definitions on page 64. Equilateral polygon, a polygon in which all of let's just think about this. Equa means equal. Lateral, if you know anything about football, lateral means to the side. So that's where these words come from. So equal-sided. So I'm going to draw my best equilateral triangle. An equilateral quadrilateral would be an equal-sided four-sided figure. So we have a square. It gets harder to draw for me, the ones, but they look very nice. This one right here, I guess, doesn't have to be a square. It could be, as long as the sides are equal length, you could have a quadrilateral still. Let's go to equiangular. Equal angles. So this is how you mark angles, like this. So if all of your angles were the same, then you'd have equiangular. So you get to regular. A regular polygon is both equiangular and equilateral. So let's just take a look at these two. This one right here was a square, and it had all four sides that were equal. It also has all four angles that are equal. This is regular. Over here, this one has four equal sides, but you could see that this angle is pretty much closed, and this one's wide open. So these angles are not the same, so don't mark them the same. So we have equilateral, but not equiangular for this one. That's called a rhombus. We'll get there eventually. It's a slanted square, basically. It says that you should, diagonal. One more. Diagonal of a polygon. Let's put that over here. Diagonal. Alright, I'm going to just put over here, it connects vertices. Okay, you connect vertices, except they can't be vertices that are right next to each other. So let's come up here. Alright, if I want to connect vertice, this one and this one are right next to each other. This one and this one are right next to each other. So what I have to do is take this one and connect it to that one. So that's a diagonal. This one is connected to that one. That's a diagonal. This is not going to have any diagonals because if I try to connect this vertice to one or the other, it's only the ones that are right next to it, and then you just get the sides. You don't get a diagonal. So the definition of a diagonal says it's a diagonal of a polygon is any segment that connects two vertices but is not a side. So you have to connect vertice to vertice, but that wasn't a side. Vertice to vertice would make a side, so that's not a diagonal. But that's the idea of a diagonal. And it says below the definitions box, it says you should now be able to classify polygons by the number of sides. You need to memorize all those names. As convex or concave, you should be able to look at it and decide if you're looking at something that's concave or convex. You're also going to have to know whether something is regular or not. And regular, in my opinion, just makes it look perfect. You'll have equal sides and equal angles. And you're going to want to know, let's see, the notation for a polygon is going to be listed in your book. You can see it right here. Let's see. The notation for a polygon is a list of the vertices in consecutive order, clockwise or counterclockwise. It doesn't really matter. But see this? You start at one of them. So you could say A, B, C, D, E. It doesn't matter which one you start at. You could start at D, but you have to list everything in order. So this could be polygon D, E, A, B, C. Just start at one spot and either go clockwise or counterclockwise. Do not go B, E, C, A, D. You don't want to do that. You need to go in order. So polygon A, B, C, D, E is a regular pentagon. That's talking about this one. B, D, and B, E. So they have them B, E, and B, D. Those are diagonals. And if they're asking if you could name 3 more diagonals. All right, then we have these last 2 things right here. The interior of a convex polygon. So convex is one that doesn't have any cave holes in it. Okay, it's something real like this. The interior is the intersection of the interior of its angles. That's a little bit, you'll want to know that definition, but I think an interior of a polygon is really self-explanatory. It's the inside. And the exterior of a convex polygon is the union of the exterior of the angles. Again, you'll want to know that one specifically, but exterior just means the outside. So that's what you'll need to know for this section. And we're going to go with we'll go with 1 through 30. 2.5, 1 through 30, all.